In order to help us graph these exponential functions, we're going to take a look at an old school method and just create a table. We'll start with the most basic value you can think of. If we here our x's, here our y's, we plug in 0. We get 2 to the 0. 2 to the 0 is 1, so we're going to graph the point 0, 1. When we plug in 1, we get 2 to the first, which will give us 2, so we'll go here, graph 1, 2. We plug in 2, we get 2 squared, which is 4. 1, 2, 3, 4. When we plug in 3, we get 2 to the third, which is 8. So we'll put this all the way up at 8, 5, 6, 7, 8, and that should be enough for our positive values. When we take a look at some negative values, something like -1, we get 2 to the negative first, which equals 1/2. So we can mark here. Now we're going to start getting really tiny in our differences. Like -2 will be 1/4. At some point we really can't get too much finer, but that should be enough. When we take a look at this, when we graph this, we're going to connect, and our graph comes out nice. It gets really steep and really small and really tiny. As you can notice, there's an asymptote here at y equals 0, or the x-axis. The reason that exists is because 2, no matter what value you raise it to, can never become a negative number. You know, even though no matter how big your negative number is, it's just going to be 1 over 2 to whatever that power is. Make it really tiny, but it'll never actually be negative, so it'll never cross our axis. When we look at 1/2, it's kind of similar, but there's just a little bit of a difference. Still, when our x value is 0, our y value is still 1. When we plug in 2 though, or 1 though, we get 1/2 to the first, which is 1/2. When we plug in 2, you get 1/2 squared, which equals 1/4. So in this case, the tail, or as x went off to negative infinity last time, is kind of happening now when it goes off to positive infinity. That makes sense because 2 and 1/2 are reciprocals. So we would expect that the rest of our graph, when x is negative, never would curve back up. Let's try it. When you plug in -1, you get 1/2 to the -1, which is 2. When you plug in -2, you get 1/2 to the -2, which would become 2 squared, which is 4. Finally, when you plug in -3, you get a y value of +8. So again, this is the same graph, except for now it's been reflected over the y-axis. I'm using these. We're going to kind of look at some what we're going to call toolbox functions, kind of like what we had with parent functions of x squared and things like that. We've got some new ones you can add. In this case, both of these functions is going to be f of x equals b to the x. The only difference here is, in this case, b is going to be greater than 1, and it looks just like what we drew. We draw a sketch here and it comes up, but we don't really know where this other point is, except for whatever it is. We'll call it 1, b. Anytime we go 1 to the right, we'll have b to the first, which means it's just b. The other point that's always there, another key point, is 0, 1. Similarly, when b value is going to be still got to be greater than 0, but when it's less than 1, we get a graph that looks like that, just reflected over the y-axis, and now we have the point -1, b. There are some key pieces of information for this case. The y-intercept for both of them. Actually, I'll write that in purple to show you that the both of these. For our parent functions, the y-intercept is 0, 1. They both have a domain of all real. X is an element of all real numbers. They both have a range where y is an element from everything from 0 all the way up to positive infinity. And they both are one-to-one functions. The only thing you need to know is when b is greater than 1, it's always increasing. And when b is between 0 and 1, it's always decreasing. Now we've looked at some of the basics of the graphs, we can see how we can actually apply these to some more difficult graphs. In this case, use the ideas of transforming functions to the graph the following function. 3x minus 3 plus 2. We can think of this as a horizontal and a vertical translation of the parent function f of x equals 3 to the x. So we can start just by graphing that. In that case, we have the point 0, 1, and we have one other point, which would be 1, 1, 2, 3. As soon as we have that, we can really just take a look at kind of what's happening with our x and what's happening on the outside. If you've heard inside or outside the parentheses, our parentheses in this case are going to be put around right where the x is, and on the outside of that is going to be this added 2. This is a translation, right 3 and then up 2. So all we're going to do is move this whole thing over. 1, 2, 3 to the right. 1, 2, 3 to 1, 2, 3 to the right, and then up 2. Up 1, up 2, up 1, up 2. With those key points, we can graph the rest. What's helpful to remember is that your horizontal asymptote is going to move too. So if my horizontal asymptote in this case is the x-axis or y equals 0, now that's going to get shifted up to become y equals 2. Finish playing connect the dots, and there's our nice little graph in the green.